let me try to get across something that maybe I didn't get across so clearly the other time. We have this theorem, properties of power series, and it said that basically that power series behaves sort of like polynomials, right? That that power series kind of similar to polynomials in the sense that if you have two power series, if you have one power series a sub n x to the n, and another power series b sub n x to the n, and you want to find, and let's say this converges in, so let's say radius of convergence r at r1 and radius of convergence r2. Okay, so the first guy converges in some radius r1, the second guy converges in some radius r2. Okay, this said that if you took the derivative of f, then the derivative of f, so one big thing was that the derivative of f could be obtained by taking the derivative of the power series term by term, right? And you end up with this thing, n a sub n x to the n minus 1 from n equals 1 to infinity. Right? And if you wanted to find an antiderivative, right? If you wanted to get an antiderivative of this guy, then all you'd have to do is take the antiderivatives term by term, right? That you get summation n from 0 to infinity. The antiderivatives of these guys, x to the n plus 1 over n plus 1 times our coefficient b sub n, right? And that if you wanted to get the power series of the product, you could get it just by multiplying these guys together as if they were polynomials. If you wanted to get the power series of the sum, you could get it just by adding them as if they were polynomials, right? This is a really useful theorem. This is a really useful theorem. So just to give an example, you remember we have 1 over 1 minus x, right? And this thing has a power series, summation x to the n from 0 to infinity. And this works in, it's valid in -1, 1. Right? Okay. So if I asked you to get the power series of -1 over 1 minus x squared, then what this theorem says is that, well, you can figure it out. So number 3, you can multiply the power series as if they are polynomials, right? So you say, okay, all I need to do to get the power series of this guy is take the power series of each of these things, 1 plus x squared plus blah, 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 and multiply it by 1 plus x plus blah, 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 as if they were polynomials. Okay, it's a little bit complicated to do, but right, x squared plus x cubed, etc. Right, it's a little bit complicated to do, but you can probably figure out how you do it. Right, you just multiply these guys as if they're polynomials. Right, we'd have how many? What's our first term going to be? Not n, nope, but it will be 1 actually, right? First term will be 1, right? Because we've got this 1 times 1, right? How many x's are we going to have? Can anybody see how many x's we're going to have? We have 2, right? We have x times 1 and 1 times x, right? We've got 2 x's, 2 x's. How many x squareds are we going to have? X squareds. Let's see, we have 1 times x squared, we have 1 x squared, we have another x squared, and then we have x squared times 1, so we have 3, right? 3 x squareds. and so on and so forth. And you just calculate it as if they were doing polynomials. Anyway, however you multiply your polynomials, you do it, and then you get some polynomial, and that power series would be the power series for this, right? Okay, so this gives us a kind of cool way of getting power series from functions that we know already. Okay, so we said earlier that e to the x has this power series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus blah, 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 blah. Right? If I asked you for the power series of e to the x times 1 over 1 minus x, you would just multiply these two power series together. Okay, so you can build up power series for functions from known power series. Okay, that's the point. That's the point of this theorem. Okay. So just to in case I didn't make it clear how useful this was, it's pretty useful. Okay. So that was basically, if you have the power series of a function, then you can build up power series of other functions. Okay. But there's actually a way to go from a function to a power series directly. Okay. So expressing functions as power series. Section 8.7. Expressing functions as power series, also called the theory of Taylor series, or also sometimes you see this term Maclaurin series. Okay. So we said this earlier. We did something like this early on in the term. I'm just going to remind you of it in case you've forgotten. Okay. So here's the idea. Suppose you have a polynomial. Okay. So p of x is some function. This function is a polynomial. Okay. But you've forgotten what the coefficients are. Okay. You've forgotten what the coefficients are. Okay. So how do you figure out, can anyone see a way of getting, how would you figure out the constant coefficient? Right? If this is secretly, 5 plus x, right? How am I gonna pick out that 5 from, how would I pick out that 5 from, if I have the ability to evaluate this function at any point, where am I gonna evaluate it to get that 5? Anna? 0. That's 0, right? So you'd say, okay, I don't know, I've forgotten what the coefficients are, but I know that, right? So I've got it's some polynomial, but for some reason I've forgotten, my brain is not as good as it used to be, I've forgotten what the coefficients are. Okay, but you say, okay, well, at least I have the power to evaluate it, so I evaluate it at 0, and I get a naught. Okay, so I know that this coefficient is p at 0, right? P at times 0, right? Right, and so how would I get the coefficient for a1? How would I get the a1 coefficient? We said this earlier. Did you remember? You take the derivative and then evaluate at 0, right? You take the derivative. I know that a1 is going to be p prime at 0, right? So I differentiate it. Right? Although I don't remember what my coefficients are, I somehow have the ability to evaluate my function at 0 and to differentiate it as well. Okay. So a1 is going to be p prime 0, right? Is that okay? Everybody see that? I hope nobody's confused by that. Okay, right? And then what's a2 going to be? A2 is going to be second derivative P double prime evaluated at 0. Is that it? Not quite. P double prime at 0. Divided by 2. Yeah, don't blurt it out. Okay, divided by 2, right? Because P prime is, of course, A1 plus 2A2x plus blah, blah, blah. P double prime is 2A2 plus, so this would be 3A3x squared plus et cetera, There's a 3 times 2A3x plus et cetera. Right, so P double prime at 0 is 2A2, right? To get A2 back, I need to divide by 2, right? I want A2. I evaluate this thing at 0, and I get 2A2, so I divide that by 2, and I get my A2, right? Okay, right? Blah, 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 blah. What's the nth? What is my nth coefficient? What do I need to do to get my nth coefficient? The nth derivative over what? Not n? N factorial, right? Over n factorial. Over n factorial, right? Because every time we take the derivative, we're going to be multiplying by, the exponent and bring the exponent down, right? So, right, E triple prime x would be, 3 times 2 a cubed x plus, et cetera, et cetera. Okay, so we need to divide by n factorial. Okay, so this works for polynomials, and because of the theorem that I said was so great at the beginning of class, this also works for power series, right? So, right, if you know, right, so you can figure out what the polynomial is going to, you can figure out the coefficients of the polynomial in this way, and you can figure out the coefficients of a power series in this way, right? So, same thing happens with power series, right? If f of x is a power series, a sub n x to the n from n equals 0 to infinity, right? Then we know you can do exactly the same thing because you can differentiate the power series as if it were a polynomial, right? So you can differentiate this guy just like it's a polynomial, and f prime is going to be summation n a n x to the n minus 1 from n equals 1 to infinity, right? F double prime is going to be summation n minus 1 a sub n x to the n minus 2 from n equals 2 to infinity, right? And so on and so forth. Right? So in exactly the same way, you get that f prime 0 is going to be, this guy is going to be, is a naught, f double prime 0, I'm sorry, is a1, excuse me. F double prime 0 is a2 over 2 factorial, and so on and so forth. So the same thing happens. The same thing happens. Okay, so this leads us to a definition. It's a definition. If your function, if f is infinitely differentiable, on some interval negative epsilon epsilon, right? So some interval negative epsilon epsilon, we call the power series kth derivative evaluated at 0 over k factorial x to the k, as k goes from 0 to infinity. The Taylor series of f centered at 0. Right. Okay, yes, Anna.
Is that a2 divided by 2 equal the second derivative? Shouldn't it be a2 equal?
Oh, I'm sorry. Yes, thank you. Thank you. Thanks. Yes, Kara.
Why is it 2 factorial and not just... Oh, is that...
It's the same thing. It's the same thing, but we write it that way just for convenience. Okay. Okay. Everybody getting it? So, if your function is a power series, then this is its power series, right? If your function is a power series centered at 0, then you can figure out the coefficients. And the coefficients, right? The coefficients, these a sub n, are going to be these guys here, right? They're going to be the kth, the kth a sub k is going to be the kth derivative evaluated in 0 over k factorial because of what we did earlier. Okay, so if your function, right? So if f is a power series, then the Taylor series is it. Is that power series. Okay. Let me put in a warning that we'll get into later. So warning, it might happen that f has a Taylor series f has a Taylor series, but that Taylor series is not equal to f. So that f of x is not equal to the Taylor series. Okay, so something strange can happen. Or something unpleasant can happen. Okay, so let me say it again. Okay, let me say it again. This might be a little bit confusing, right? So here's what the story is that if your function is a power series to start off with, then the Taylor series is that power series, and so your function is those things agree. The function is the same thing as the Taylor series. Okay. But it may be that your function doesn't have a power series expression. In that case, it might be that your function has a Taylor series, but that Taylor series is not your function. Okay. Okay. So the Taylor series doesn't necessarily give you back your function. Okay. If your function is a power series, then it works out. Okay. But if it's not, then all bets are off. Okay. You might not get back your original function. Okay. Okay. We'll give you an example of that in a second. Okay. Okay. So let me also make a remark that we can do this. We can also do this. The theorem is also valid for when centered on some other point. When centered on some other point not equal to 0. Okay. I'm sorry, the definition is also valid. Okay, so we can also talk about Taylor series centered on some other point. Yeah, this guy.
Quick question.
Yeah.
You say that it's not a power series. Do you imply that the Taylor series then approximates the actual function?
It may not at all.
Or not even at all?
Yeah, so they may be completely unrelated. So you can have something bizarre that you've got a function, and that function is infinitely differentiable,
Yeah.
and so you can get a Taylor series out of it. But that Taylor series is not related to your function at all. Okay, yeah. So strange things can happen, and we need to figure out when they do happen, or some conditions that prevent them from happening. Okay. So getting back to my remark, we could also do this for a Taylor series centered at some other point A. Okay. So in that case, our Taylor series would look like this. It would be, instead of this thing, you would have x minus a to the k. And you would evaluate this thing at a. Maybe I should write it out again. So you would end up with the kth derivative evaluated at a over k factorial, x minus a to the k. K goes from 0 to infinity. And this would be Taylor series centered at a. Taylor series centered at A. Do you have a question?
Oh, no.
Okay. Here, let me give some examples. Examples will bring it all down. So here's an example. Our function is e to the x. E to the x. This is definitely infinitely differentiable. Right? F is infinitely differentiable. When you see something like this, C infinity, it means infinitely differentiable. C2 would mean twice differentiable. Okay. So if I say, what's the Taylor series for F centered at 0? What's the Taylor series for F centered at 0? Well, it's just going to be this thing, right? Summation kth derivative valued at 0 over k factorial x to the k from 0 to infinity. Right? So you just evaluate these derivatives, right? Right? So you just need to figure out these derivatives. What's f at 0? Well, that's e of 0, which is 1. Right? What's the first derivative at 0? Anna? Just take the first derivative of e to the x. What's the derivative of e to the x? E to the x, evaluated at 0, get e to the 0, it's 1 again. Second derivative, take the second derivative, evaluated at 0, you get 1 again. Keep on doing this, stop after a few times. You realize that it's always going to be 1, right? And so the Taylor series for the Taylor series is going to be summation 1 over k x to the k goes to 0. Okay, so this is the Taylor series for e to the x. So if we hadn't done some work last time, all we would know is that there's this function e to the x, and there's this Taylor series, and we don't know if they're equal to each other. Okay. Last time, however, we saw that this function actually is e to the x. Okay, so it turns out that the Taylor series for e to the x actually gives you back e to the x. Things are good. Okay. Okay. So.
Can you say that again?
Yeah. So last time we saw that this function actually is e to the x. Okay. If we hadn't done that work last time, then we actually wouldn't know if this function gives you back e to the x or not. Right? Right? We have our function, we have our Taylor series, but we actually don't know that those things are the same thing, except because last time we already saw that this is e to the x. Okay. Okay, but the main thing here is, does everybody see how to get the Taylor series? Right? You just take your function, differentiate it, evaluate it at 0, you make a series out of it. That's your Taylor series. Okay. What about Taylor series centered at x equals 1? Okay. Well, again, following the formula, I need to take the derivatives, evaluate them at 0, and then divide by k factorial. Take that times x minus 1 to the kth power. Okay. I hope that doesn't happen often, but okay. Right, often or like en masse. Okay, so you take the kth derivative, right? Kth derivative is, you know what it is, right? Kth derivative of e to the x is e to the x. You evaluate it at 1, you get e to the 1 every single time, right? So the Taylor series, I'm going to do some bad board work here. I'm just going to put in, it's just going to be, this is it. Okay, so the Taylor series centered at 1 for e to the x is this guy. Okay, right. So right, it just looks like e times, right? So you've got this is it. Okay. Okay. Let me make you do one. Suppose I'm considering the sine function. Suppose I'm considering the sine function. Okay. This is an infinitely differentiable function, right? What's the expansion? What's the Taylor series expansion about 0? Okay. Take 1 minute and calculate it. All that's involved is taking a bunch of derivatives. Okay, turn to somebody nearby and tell them what your series is looking like. Sorry, I just saw this really sort of dubious look between two people. Don't do Okay, let's do it. Let's do it. So this is it, right? This is it. All you need to do is calculate the derivatives of the function, right? Well, what's the, you got the sine function, you evaluate it as 0. What's the sine at 0? 0. Then you take the derivative of the sine, right? So this is f at 0. F prime at 0 is going to be cosine of 0, which is 1. F double prime at 0 is going to be negative sine 0, which is 0. Right? F triple prime 0 is going to be negative cosine 0, which is negative 1. F quadruple prime, which we just read before, is going to be negative sine, right? So we get 0. And then you realize that you don't need to go on any further, right? Because the fifth is going to be cosine, and things start to repeat, right? And you don't want to do anything repetitive in your life, right? Okay. So the pattern of coefficients is going to be 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, etc., etc. Okay. Right. So what does the series look like? It's going to be 0 plus 1x plus 0x squared right? Plus, I mean, maybe I should say 0 over 2 factorial x squared plus negative 1 over 3 factorial x cubed plus 0 x to the 4 plus 1 over x to the 5, x to the 5, etc., etc. Right? In other words, the Taylor series for the sine around 0 is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus blah, 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 blah. Okay, that's a Taylor series for the sine. Okay. In fact, this is the sine. So I will see how you can figure that out later. So what I said was that you have your function and you have your Taylor series, and you don't know that this thing actually gives you back your original function. But in this case, it actually does. We'll see why next time. Okay, let me just give it to you as a fact for now, and we'll back that up later. Okay. If you know this is the sine function, then what's the cosine functions? What's the cosine function's Taylor series?
It's the derivatives.
The derivative, right? So in fact, cosine is going to be 1 minus 3x squared over 3 factorial. Well, that's x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus minus, etc. So if you actually know that this is the sine function, then you can get the Taylor series for the cosine function. Okay. Yeah. So let me also write this more concisely as -1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. As k goes from 0 to infinity. I hope that makes sense, right? We're letting k go from 0 to infinity, and we're taking only the odd powers, right? We're taking only the odd powers, right? 2k plus 1 as k goes from 0 to infinity, that will hit all the odd numbers, right? That's going to hit all the odd numbers. You divide by the odd numbers factorial, and we have this alternating sign on it to make it the right sign. Okay, so I hope you see that getting the Taylor series associated with a function is not that hard, right? All you do is just take a bunch of derivatives and use those guys to make your coefficients. Okay, that's it, right? Okay, so again, the reminder that nothing guarantees that the Taylor series of f converges. It might actually diverge. It might have yeah. So or even if it converges, that it converges to f. It may be that your Taylor series converges, but converges to a different function. Okay, so this is a little bit strange, but so things don't always work perfectly.
This is or even if what converges.
Even if it converges, even if that Taylor series converges, that it converges to f. Okay, so nothing guarantees that it converges, or even if it converges, that it converges to your function. Okay, so let me just give you a case where things go bad. The function e to the -1 over x squared e to the -1 over x squared, where x is non-zero, and 0, where x is 0. Okay. So this is a function that becomes very flat. Okay. Becomes very flat as you get close to the origin. Right? Because as you get close to the origin, this is e to the -1 over basically infinity. Right? So, and e is this fast function, right? So it's shrinking incredibly fast. Okay, so it's very flat as you get to the origin. Okay, this function is infinitely differentiable. This function is infinitely differentiable, and all its derivatives are 0. All its derivatives at 0 are 0. All its derivatives are 0, so its Taylor series is 0, right? You've got summation of 0, all the coefficients are 0, right? So the Taylor series is just 0. Okay. The Taylor series is 0. That's a good Taylor series, converges everywhere, but doesn't give you back your function, right? Doesn't give you back your function, except at 0 itself, I guess. Okay, so things can go badly. right? Things can go badly. Your Taylor series, you've got your infinitely differentiable function, but the Taylor series isn't at all the function, right? It's not the function, right? So the question is, how do you know, right? How can you tell if the Taylor series actually converges to the Taylor series of f actually converges to f, right? Okay, next time we'll give a condition using something called the Lagrange remainder theorem. Okay, that will say if this sort of thing happens, then your Taylor series gives you back your function. Okay, so we'll give a condition on the function that will guarantee goodness. Okay. Okay, that's it for today.